Hello PSCC 2020. My name is Mike Heyns and I have the pleasure of presenting some recent work done by the UCT SANZO work group on GIC modeling for power systems. Now, I know this isn't a live presentation, so really looking forward to getting stuck into things a little bit later in the question and answer session. For now though, let's go through the presentation. Before we get into the nitty-gritty, I'd just like to acknowledge my co-authors and colleagues at UCT and SANZO who contributed significantly to the work you'll see here today. Also, since none of them are here to defend themselves, they can take the blame for any errors in this presentation. The goal of this research has been to take existing GIC modeling methodology and optimize and improve on it using empirical approaches. In these empirical approaches, using measured data, we also aim to provide an operational perspective. The title of our paper is Data-Driven Transfer Functions and Transmission Network Parameters for GIC Modeling. Now, that may seem like a bit of a mouthful, and it probably is. And for those of you who are not familiar with the term, GIC in this case refers to geomagnetically induced currents. GICs are naturally occurring currents with their root in space weather and the sun. Over the 11-year solar cycle, large solar storms can occur, which eject huge amounts of plasma into the solar wind, which can in turn interact with Earth's magnetic field. This interaction causes large-scale fluctuations in the Earth's magnetic field, which through Faraday's law of induction can induce electric fields on the Earth's surface. Given a large grounded conducting network such as a power grid, these induced currents can cause real currents in the grid with detrimental effects to transformers. At a transformer, the GICs can be modeled using a very simple nodal equation given in equation 1 here. At a time t, GICs can be related to the induced electric field in the northward and eastward direction. Is the traditional modeling formulation, which takes the B field or magnetic field and assumes through some transfer function an electric field and then applies network parameters for alpha and beta to get GIC. Another approach is that of transfer functions, which go straight from the B field to GIC. In terms of the E field derivation used in traditional modeling, the ground conductivity is taken into account the surface impedance tensor, which relates the E field and the B field. Although the state of the art currently in geophysics is three-dimensional tensors, which take into account large magnetotelluric surveys, we restrict ourselves to a very simple 1D approximation, which can be applicable to any utility. At the heart of the methods presented in our paper is the fact that we use empirical or measured data. All the factors unknown or unmodeled in the traditional modeling, which includes the geophysical assumptions made in the geoelectric field estimation, result in errors. These errors have to be acknowledged. Starting with the governing GIC equation, equation 1, we can acknowledge these errors by including error terms. On the left, GIC includes an error term which would probably be largely due to measurement error. On the right-hand side, both E-field terms also include errors. These error terms can further be grouped to replicate equation 1, or the governing equation. The result is something very much what we see here in equation 4. Gamma is the measured GIC, and it is related to alpha and not A, EX, and beta, not B, EY. These alphas and betas are no longer constant single network parameters, but rather ensembles of network parameters that absorb measurement and modeling errors. Assuming independence over time instances, we can solve for alpha and beta using pairwise combinations of whatever time series we want to use. The result of the ensembles aren't fact distributions, as can be seen here for the alpha parameter at paradise. Described further in the paper are also the different regimes of network parameters. These different ensembles were trained using different levels of GIC strength. For the blue case, as can be seen here, we have a 0 to 10th percentile GIC strength, or in a cumulative distribution of Paradise GIC data, it will be this portion here. For modeling purposes, the total ensemble at Paradise was used. Out of interest, the ensembles are heavy-tailed, and hence the median is the best measure of central tendency, and the interquartile range is the best measure of spread. A large benefit of the ensemble methodology is that for a limited data set, there are a large number of ensemble estimates that can be produced. Given an hour of 2-second cadence data, around 1 million estimates are produced. Convergence is much quicker for minute data than for 2-second data, as can be seen here by the blue minute data and the 2-second cadence data in red. In terms of data, 3 international data sets were used. The South African data is from the Halloween storm, and unfortunately during that time, only 1 minute B field data was available. What is very interesting is that the US and Australian data comes from exactly the same event. This means we can actually see the GIC response from very different parts of the world. For all data, 25% of the data set was kept out for validation. This is in order to align with previous modeling done in the South African network, to which we compare in our paper. That said, this 25% includes some of the trickiest parts of the storm, which means we've set ourselves up for failure in terms of modeling. Nevertheless, our modeling method overcomes this and is shown to be operationally effective. An interesting implication that came from this research is that data cadence definitely does matter. In the past, 1 minute data has often been used for GIC modeling. This, however, cannot represent all GIC dynamics. As can be seen in the high-resolution data from Australia and the US, there's a lag in the sudden storm commencement across the globe. Also possible, but very much dependent on the derivation of the E field, is a lag between the E field and GIC. Besides modeling, the ensemble method can characterize the network susceptibility and directionality. Susceptibility is linked to the magnitude of the network parameters, and the directionality is in turn the effective direction that, when aligned to the E field, will produce the largest GIC. This effective directionality does not just include local lines, which are the dotted lines here in this figure for Bower North in Australia, but rather includes the entire network weighted along with geophysical aspects. An alternative formulation to traditional modeling, but still appropriate given measured data, is that of the transfer function approach. Here, instead of relying on the geoelectric field and assumptions made about the ground conductivity structure, we relate the B field directly to GIC through a transfer function with two transfer function components. Equation 6 relates those two components to their associated B field values to get network-weighted current terms. This approach can be extended in the time domain due to these network-weighted current terms, and similar treatment to before can be applied. Instead of network parameters, dimensionless parameters G and H can be used to derive ensembles that tweak the modeling and include uncertainty in their spread. A result of the simple transfer function with its components is shown here for the grassroots substation in the South African network. The top two panels show magnitude and the bottom two panels show phase. What is very interesting is the effect of the signal-to-noise ratio in the left-hand side. Because the network is north-south aligned, we would assume a north-south geoelectric field or E field would be the main driver. The actual orientation of the E field and B field largely can be thought as orthogonal. So although that it's north-south lines, it is the east-west magnetic field or the TY component of the transfer function that has most weight. Taking the different methods into account, we can see the operational usefulness in terms of modeling. Here, to be comparable with previous modeling in the South African network, the relative error is defined. This is the median value of the relative error in percentage of all time instances over 1 ampere GIC strength. In terms of grass ridge, the layered earth or traditional modeling performs better than any previous modeling done. The transfer functions, however, incrementally improve on this, which can be expected since less assumptions are made. Bowen, in this case, is included for consistency, but lacks enough data for proper transfer function analysis. Paradise, on the other hand, is very interesting. Here we have the layered earth or traditional model that does relatively well, but then the transfer function approaches do worse. Although there's a slight incremental improvement in the updated transfer function with the original. This issue with modeling can largely be attributed to the 1,000-kilometer separation between the magnetometer and the power network in the Paradise model. Given this separation, there were unexpected localized disturbances that made a large part of training. These disturbances are geomagnetic pulsations, as seen here by the red part of this diagram. Pulsations are not typical drivers of GICs, where most GICs are located at the sudden storm commencement or the main phase of a storm. At mid-latitudes, the disturbance B field is generally assumed to be close to that of a plane wave. These localized disturbances unfortunately break this assumption, and the spatial scale is drastically reduced. Furthermore, these pulsations have an intrinsic frequency dependence to them, and thus the transfer function approach, which is in the frequency domain, is more effective than the layered earth approach that is purely in the time domain. Regardless, the ensemble methodology allows the methods to absorb error and translate it into uncertainty, or, in this case as shown, an uncertainty band. Given any setup, even with a large separation between magnetometer and network, the ensemble methodology will give an actionable result with associated uncertainty. That said, this uncertainty may be very large. Out of interest, this particular figure is the validation set for the grass ridge data set, and the two shaded periods have been defined in previous work as periods of intense GIC activity. From this whirlwind tour through data-driven GIC modeling, there are a couple of take-home points. The first is that given measured data, the simple nodal GIC equation can be used to model much more complicated GIC dynamics and absorb error when assumptions break down. This can be done with limited coverage in the network and no further information about network or ground conductivity. Furthermore, uncertainty is included in the ensemble methodology, which is ideal for operational application. These empirical network parameters can be used to test transformer-level models and augment other more general network models for GIC modeling. Up to now, empirical GIC modeling has largely been overlooked due to a lack of data. But due to the FERC Order 830, this may become a thing of the past as more and more utilities collect data. In the paper, there's a reference list of GIC literature that goes into far more depth than this condensed presentation. I'll urge anyone who's looking for bedside reading material to go through these papers. I'd also like to acknowledge funders and providers of GIC and geomagnetic data. Without these players involved, our research just wouldn't be able to happen. All in all, I feel the next big steps in GIC modeling is that of data-driven models. It will be very interesting to see what the next few years holds in store. As I'd mentioned earlier, if we don't get through all the questions in the question and answer session just now, then please do reach out to any of the authors on the emails in this slide. With that, thank you very much.
Okay. This was a first time experiment. So I didn't have time, of course, during this to see the Q&A. So maybe, Mike, you can look at them as well. We have a short time to answer some of them.
It seems quite quiet on the Q&A from our side.
So you have no questions? Okay, then I would like to thank you for your presentation, and for the sake of time, we have lost a little bit time in this procedure. We will go to the next speaker. Thank you.
Thank you very
Louis,
much.
I have a question if I could ask it quickly.
Yeah, of course.
So I'm curious, Mike, how would you, or do you see there's any straightforward way to incorporate some of the models you're creating in like in an optimization framework? If you're trying to make decisions to redispatch the system based on, you know, the models that you have, is there a straightforward way to do that, or is that a challenging task?
I think it's something that is undergoing a lot of research in other fields, where exactly to be putting in the results of GIC modeling in systems. And that stems a lot from what type of mitigation techniques the different utilities have available and would like to implement. So it's not a trivial thing. It's not something you can just plug in, but you can do a lot of planning and that kind of research, taking into account some of these results and obviously for extreme value assessment and risk. So yes, there has been work done, but from a day-to-day perspective, I'm not sure how many utilities are currently doing anything with GIC modeling.
Thanks, I appreciate it. It's a really interesting approach.
Okay, so thank you both of you, and especially Michael for his presentation.